Hello, this is Cyprian from Midas IT. In this tutorial number 3 for Midas Gen, we'll see together how to analyze this web opening detail analysis, how to simulate it, and how to get the results. So all the things that I'll study with you together are: I'll show you first how to study plate elements and to get the stress distribution around the hole. Then I'll show you how to assign rigid link and how to link this detailed plate model with beam model. And finally, I'll show you a method to extract analysis result for the plate elements. And also, so I'll go through the 7 steps that you can read on this page: preference setting, material and section properties, structural modeling, structure support condition, and then enter the loading data, perform the structural analysis, and interpret the analysis results. On the right, you see the analysis model that I will create. So let's go. Okay, so now as you can see here, I'm on the start page of Midas Gen. I just opened the software. So now let's create a new project. So once my new project is created, I have to check the unit system and change it as I want. So in my case, I'll use Newton unit and meter is okay. So it's great. Okay, let's do like that. The next step is to create the user coordinate system. So in this case, I want my beam to be in the XZ user coordinate plane in order to coincide with the global coordinate system. So to do that, I'll go into the tab structure and I check XZ plane, and I will define this plane along to origin 0, 0, 0 and with a rotation angle of 0. So click on OK, and you can see now that it is oriented like that. So actually the user coordinate system X, Y corresponds to the global coordinate system X, Z. So let's check the front view. Okay, and now I can start the next phase. Let's enter now the material and the section properties. So let's go in the properties tab and click on material property. So in this window, let's create the material first. So click on add to add a new material. Type of design steel is okay. The standard will use standard AST MS, and in the database here we'll choose the section A36 and just click on OK to add this material to the database. Now let's input the thickness because I will analyze plate material. So the plates that I will create, the thickness are in millimeter because I create 4 different thicknesses of 10 millimeter, 15, 20 and 40 millimeter for the pipe, the stiffeners, the web and the flange. So this will be in millimeters, so I have to change the unit in millimeter before adding thickness, and now you see that it's written millimeter. So be careful when you do that, otherwise you'll have strange result afterwards. So for the thickness ILD, I'll just put 10, so it will be very easy to recognize that this will correspond to the 10 thickness plate. So click on apply, and let's just add the other 3 thicknesses. So 15, 20, and 40. And OK. And now let's change again to matter. Okay, and close that. So now what I'll do is that I'll create 9 nodes that will be used as the basis to create my web opening. So as this web opening is symmetrical, I only create half, and then I'll use the symmetry function to create the other parts. So let's start. So first of all, activate here in the small icon bar the display node number and displayed element number. This will be useful later on. And then go in the tab node element and click on create node here. So create your first node at the position 0, 0, 0. Apply. So you see it appeared here. And after you did that, select translate node. The node here should be selected. Use the function unequal distance, not equal, and we will translate this node in first the x direction. So that's right. And you can enter an array of values to define and to copy at several positions at the same time. So we'll copy at 0, 8, 0, 7 meter and click on apply. Oh, no selected node. Okay, I forgot to select the node. So select the node like that, apply. So now the 3 nodes are created. I'll use the function here on the right, auto fitting. So now I have the 3 nodes on the screen. Now let's copy those nodes in the y direction. So in this time I select y, and the distance will be 0.7, 0.3. Click on apply. So okay, and now what I need to do is to move this so the distance here will be equal to the distance between these two. So let's select the first node here. Let's not copy it but move it this time, and let's move it in the x direction at 0.5. Apply. Okay, that's done. So now I have my 9 nodes, which will be the basis of my web opening model. Now let's create our plate model. So first thing I'll do is that I will extrude this node 1 into a rotation around this axis like that to create my first beam, to create the beam of the opening here. So let's go in the node element, extrude. Let's select the node here, the node 1. So to select it better, you have to use select by window option, like that. Then here select node line element. So you have several types. You can extrude a node into line, line into planar, planar into solid. So here we'll extrude node into line. The type of element created will be beam. Material will be A36. So for the section here, what I'll do is that I will enter a section number 999, because actually this beam will be deleted after when I create my plate. So I don't really need to define the section properties. So I'll just enter that and this will be deleted. Generation type, so we'll generate that by rotation, and we'll use the equal angle method. We'll extrude that 8 times, and angle of rotation will be 90 degree divided by 8. So each time it will do like that. The axis of rotation is Z, and okay, the first point, which is the center of the axis, is 0, 0, 0. So click on apply, and that's done. So I have my first beam here. Now I want to create 8 plate elements between this beam and those 3 nodes. So you see probably that I need more nodes between these 3 nodes, otherwise I cannot connect the first plate element here. So to create these elements, what I'll do is that I will divide these nodes and add here. So you can do that. Go into the node section and you have a function called divide node. So it's here. Uh, I'll choose the number of division of 4, and here I have to select the node to divide. So I just select the first node and the second, and you see that 1, 2, 3 nodes have been created. Similarly, I select this one, and the nodes that I want are created. Now let's have fun and create our plate elements. So click in create elements, and here we'll create plate. The material is A36 and the thickness is 20. So you see that I'm using here the thickness property that I defined previously. So you have to click here in this nodal connectivity button, and the only thing you have to do is to click like that on the different node to create the 8 plate elements. So I already created 4. Okay, almost done. Okay, so and now that I've done that, you have a small icon called shrink in the tab bar. So if you click here, it's actually a bit better for the visualization because you can see the node IDs here, so it's more clear after. So I'll just use this option. Let's just zoom out a bit, and now I'll create the elements here. So let's do the same, select the nodes here, but before I select that, I'll just have to uncheck the option intersect, otherwise the plate I create will be automatically intersected, but I don't want that. I will divide it by myself later. So I select like that, 1, 2, 3, and 4, 1, 2, 3, and 4, and 1, 2, 3, and 4. Now let's divide our elements. So you have function divide here. So I'll select that. So to select those elements, I'll use this select by intersection. So I draw like that, and you see those elements are selected. Now here element type, so here planar. I'm dividing along equal distance, and the number of division along x is 3 and y is 1. Apply. Okay, now that's divided like that. Now let's select the plate here, and this one has to be divided into 4 and 4 like that. And let's select these two elements here, and they have to be divided 4 and 2. Apply. Okay, I think I have a small problem here, so what I'll do, I'll come back. So let's do one at a time. So X, Y, okay. And this one I think maybe I have to do 4 and 2 like that. Okay, done. Okay, now let's create some beam that I will use to extrude a plate in the perpendicular direction to this plate. So I will generate the stiffeners, horizontal and vertical like that, and the flange. So let's go into element and create element. This time I'll use general beam, tapped beam, and so it's for the section I'll use 998, and I just have to select my beam. So first for the flange, so let's select the two nodes. I have to, before I do that, I have to check like that I'm intersecting the nodes. So I click here, so you see that I generated my first beam, and now it's very important, I have to change the section to 997. I'll show you later why, because I extrude with different properties. So, and click on the nodal connectivity again and select like that, one time here and one time here, to generate the horizontal and vertical stiffeners. Okay, now that I got this part of the model, let's use the mirror function to create the full model. So go into element, mirror. Let's temporarily hide the node number and the element number. Let's select all the nodes, and we have to do a copy of these elements. So the mirror plane is XZ at 0 position. Apply. Now let's do again. So let's select again all the elements, and along YZ plane do another copy to get the full model. Okay, now it's time to go out of the user coordinate system and to extrude this. So let's go into the isometric view like that, and go in the view, and let's come back to the global coordinate system. And now in the works tab, so let's close that. So go in the works tab here. You see you have the three sections which are undefined, so which represent the beams that need to be extruded. So let's select the section 999, which represent the pipe-shaped stiffener, and then let's go into element and extrude this. So I have to extrude that line element planar. Let's remove the source, so it will automatically remove the beam that I created before. I want plate element with material A36, and the thickness is 10. Confirm. Okay, I will translate for the generation type, and the type is equal distance. So I have to enter the coordinates here for the translation. 0 minus 0.1 and 3 times, so which means that it will create 3 elements in the thickness, and it works. Now I just have to do the same for the two other beams that I have here. So now the work menu is hidden because I'm using this, so I'll use another way to select these elements. So you have something called select identity elements, so this small icon here. So, and you can here select the section. So here you have to select the section 998, add. So, okay. So this is the section of the flange. So this one has a thickness of 40 and has to be extruded 4 times. So let's just apply that. Okay. And let's do the same thing again. Select by section, and now I have only this one left. So those are the vertical and horizontal stiffeners that have to be, so they have a thickness of 15 millimeter, and there is 3 times extrusion. Apply. Okay, so that's it. And finally, to create the full model, I'll just have to mirror everything except the web. So to do that, let's select everything, and then let's go into the work menu and right click, unselect. So now as you see, only the stiffeners and the flange have been selected, and now I can use the mirror function to mirror those elements along to Z, X plane at 0. Okay, and that's done. So let's take a look. So now I created my full model. Now that the detail model is completed, I'll create the beam which will be linked to this detail model. So go into create node, and let's create a node manually. So the first node will be of coordinate -3, 0, 0. Enter 1 in the number of times, so it will be copied, and the distance of the second node will be 9, and just click on apply, and you see that it created the two nodes, one here and one there. So now let's create the element. So element, create elements, general beam, tapered beam. So confirm, and here for the section we'll have to create a custom section. So click on the small icon here and in the section tab. So before we click on add, we have to change again the units because we are in meter and the section will be in millimeter. So go in the small unit here, change to millimeter. So this is very important, don't forget to do that. Add db user, we'll do I section. Let's create a user section. So the name will be I 2000 x 800 x 10 bar 40. Then let's enter the different parameters. So the h is 2000. Then the b1 is equal to 800. The tw is equal to 20, and the tf1 is equal to 40. So that's it. Okay, my new section is created here. Close, and you see that this has been automatically assigned here. Now don't forget to come back to meter unit. Okay, and now we just have to select the right node, check that nodal connectivity is checked. Okay, and click this node and this node here. So we created the first part of the section, and this node here and this one, and now we created the second element. Now let's close that and let's assign the structure support condition. So we'll begin by specify the pin joint support condition at the both ends of the beam. And before we do that, I just hide the section and okay, and cancel the shrink. So we'll have a model like that. It will be more easy to assign the boundary conditions. So for the boundary condition, let's go in boundary and let's click on define supports. So we'll have to block the 3 translation, and we have to block the rotation along x-axis. Then click on select by window and select like that the 2 ends of the beam and click apply to apply this support condition. Now the next thing to do is that we have to link this beam with the detail model by defining a rigid link. So basically we have to link this node here to all the other nodes of this side. So to do that, let's click on rigid link. In the master node tab, you have to select the node which will be at the center of the rigid link, and then typical select rigid body, so all the degree of freedom will be selected. And now we have to do is select all the nodes which are inside this plane. So to do that, you have a selection by plane like that. So select the plane YZ and the position X here, and you see now that all the nodes here have been selected, so that's good. And now we just click on apply and you see that the rigid link has been created. So now do the same at the other side. So here the master node is this one, and rigid body we have to select again, so let's use the same function. So YZ, select again this node and click on apply, and our second rigid link has been created. So now that the model is almost finished, let's define the loading. So first of all, let's define the loading cases. So go into the load tab and click on load static cases. Here let's call it beam load, and this is an user defined load. Click on add to add it here and close this window. Now let's define the uniformly distributed load on the 2 beams. So let's use select single and select the 2 beam element on which will apply the beam loads, and go into load tab and you have something called element element. So that's here. So load case is beam load, add uniform load, and the W will be minus 50,000, and click on apply to assign the two uniformly distributed beam loads. So now we have to define the concentrated load on the detailed model on this part here. So to do that, what I'll do is that I will activate only the nodes from this face first. So let's use select by plane, select XZ plane, select a node which is inside this plane like that, close, and click on the button activate. So now you see only these node have been selected. Now you can use the zoom if you want, but I think for me it's okay like that. So what I'll use is, you have an option called select by polygon, yeah, this one, and now I have to select the node from these faces, but be careful, you shouldn't select the two end nodes, only the nodes from the middle. Why? Because the concentrated load at the two extremities has to be divided by 2. So okay, so I selected like that. Now go into load and you have nodal loads like that. So confirm that the load case name is beam load, and in the FZ field enter the value of the load, which is minus 50,000 multiplied by 3 divided by 16, and click on apply. So and now I just have to select the two end nodes here, this one here and this one here, and this time I have to divide this value by 2 because it's the end nodes. Apply, and that's done. Now I can activate again all the elements. Okay, and that's it. I can activate the value of the load in the display window. So go load, and here select beam load. So yeah, beam load here, and nodal loads. Okay, I still don't see it. Okay, I have to check this option, load value. Click on OK, and now you have the value of the load, so you can check if this value is correct. So now everything is ready, and I can go and perform the structural analysis. Okay, let's close that, and let's go in analysis and perform the analysis. So now the solver will do the job, and that's already finished. So now I am in the post-processing mode. So remember, you have a pre-mode and post-mode, so you can see it here, and the result will be inside this tab here. So if you want to modify your model again, you have to go back to the pre-processing mode by clicking on this icon, or to clicking on F7 on your keyboard. So now we can start by visualizing and interpreting the analysis results. So let's start with the member stresses. So first of all, let's activate again the section that has been hidden. Let's okay, and go in result stresses here, and choose plane stresses. Now in the tab here, select sigma xx component, and in the type of display we want the contour, the legend, and for the unit, let's view in kilonewton and in centimeter. Apply. Okay, so now we have the stress contour for the plate element inside my model. So in MindasGen you can auto compute the member stresses, so it's necessary to have that for design purposes. So you can use the local direction force sum function to compute the element forces automatically at the boundary between the beam element and the detailed model. So let's take a look and see how you can do that. So let's go back to initial view. Let's do a zoom like that. Now let's go into display option, draw, and the hidden model, select outline. So we have a view like that. Now in result detail, choose local direction force sum, and in the mode we have to select plate edge polygon, so polygon selection like that. So confirm that the load case is ST beam load. Let's toggle off the section, and now what I have to do is activating the nodes. Okay, and no, okay, like that. So now I have to select the nodes like that off. Let's rotate and do a rectangle. So you see that the position have been recorded, and click on calculate, and now you see here that the local in the result output that the member stress in the local direction has been computed. So this sum of all the nodal forces contained in a specific section is computed at the centroid of the section according to the local coordinates defined on the section for which element forces are to be computed. The computed value of the strong axis bending moment, my, for the member at the right end of the defined model is 506. So here I have to put again in meter, so you can meter, yeah, so you can see it. Okay, so it doesn't change, so I have to select again. It doesn't automatically update the value. So for that you have to change the unit before actually calculating. So you see now the value in kilo Newton meter is 506.25. Now let's close this and let's compare this value with the value computed on this side of the beam. So for that, go in result, forces, and select beam forces and moments. Then let's view contour, so click here and type of display, check reverse contour, and now you have the value that is outputted. So if you move the mouse at the middle of the beam, you see in the window that is outputted that at the I end the moment my is equal to 506.25, which is exactly the opposite of the one we calculated on the detail section, which means that it's correctly calculated. And that's it for this tutorial. I hope you enjoyed this video and that you learned how to use Midas Gen to do the detail analysis of a web opening model. Thank you very much for watching.